Hello everyone, welcome to my channel Math 6 IIT Academy. So let us discuss about set language. So first of all, let us come to the definition of set. Set, it is a collection of well defined objects or elements. So here well defined means this particular objects is belongs to this collection or not. So that is a work of well defined here. So sets is always denoted by capital letters, denoted by capital letters, and elements of the sets are denoted by small letters. Okay, so here let us see one example, and with that example it is very clear to understand about set. Okay, so already I told you that sets is always denoted by capital letters. So here I am taking capital A, and simple example I am taking, and which is consisting of 1 2 3 4 numbers. So in this collection 1 2 3 4, we can say which elements or which numbers are present in the set or the collection. So here all these 1 2 3 4 are belongs to the collection. So this collection is well defined. So this particular collection we can say it as set. Okay, so like this we can consider so many examples. So suppose I am taking a B is another set because it is also capital letter and it is denoted by capital B here, and I am taking small ABC. Okay, so here this is also, this collection is also a set. Okay, so now we will see the example for not a set. Example number 3. Now suppose I am taking C here, and C set I am defining like this: the collection of most talented players in a cricket, in a sports or crickets. So here this most talented is not well defined, because here the opinion of the persons are different on one particular player or some particular players. So here the most talented is differ by person to person, so it is not well defined. So hence this particular collection of most talented players is not a set. Okay, so like this we can consider so many examples, like collection of all most talented writers in India, or the collection of most dangerous animals in the forest. So here most dangerous, talented, most beautiful. So all these are not well defined. These are different by person to person. So it is not well defined. Okay. So now let us see the next representation of set. Okay, so we have two ways to represent a set. One is roster form or table of form. Okay, so first we will see this roster form, and after that we will go for the next. So in this roster form, simply we list all the elements of the set, and the elements are separated by commas and which are enclosed within the braces, means curly brackets. Okay, so here I am taking simple example, that is here suppose 1 5 7 So here these are the elements 1, 5, 7, and these elements are separated by commas and which are enclosed by braces, okay, or curly brackets. So this is the set in the roster form. Or you can take one more example. Suppose here I will take the vowels in English alphabet. So here vowels are A, E, I, O, U. So here we have to write A, E, I, O, U, and these elements are being separated by commas and which are enclosed within the braces. Okay, so this is the representation in roster form or tabular form. Next we have set builder form. Okay, so in this set builder form we will give some specific rule, and that rule which is satisfied by all the elements of the set and which is not satisfied any other element which is outside of the set. Okay, so that particular rule or conditions we will implement in the set. So that form is called the set builder form. Okay, so here the same example 2 I will write here in the set builder form. So here V means set of all vowels in English alphabet. Okay, so that in the sense what here, suppose otherwise here you can give any variable, and usually we'll use to write like this. So here first we have to give one variable, and this is such that symbol, and we have to give the condition on this variable x. So here x is vowel in English alphabet. Okay, so here you will get ultimately this only. Okay, so this is the set builder form. Okay, right. Next we will see types of set. So first of all we have empty set or null set or void set. Okay, so we have three names for this. And if a set is said to be empty set if it doesn't contains any elements. Okay, so if a set does not have any element, is called empty set. Okay, so this empty set is denoted by the symbol pi or empty braces. Okay, it is denoted by pi or empty braces here, and we'll see one example. Suppose here I am taking one set, and here in this of course I am writing in set builder form. So here I am giving x is a variable such that x is an even prime number greater than 2. Okay, so x is an even prime number which is greater than 2 means here we have only one even prime number, that is 2. So we don't have any number which is greater than 2. So here simply we will get empty set only. We don't get any element. So there is no element present in the set A. So here A is called empty set, and simply you can denote it with this empty braces or you can denote with pi. Okay, so this is about empty set. Next, finite set and infinite set. Okay, so if a set contains a finite number of elements, are called finite set, otherwise infinite set. Okay, so we'll see the example, and with this example we'll understand what is finite and what is infinite. So simply the set contains finite number of elements or definite number of elements. So here I am taking minus 5, minus 2, suppose minus 1. Okay, so here we can count easily 1, 2, 3 numbers are there. So here elements A have, sorry, the set A have only finite number of elements, so it is finite set. Okay, so now when you are taking a set of all natural numbers, so set of all natural numbers starts with 1, 2, 3 and it will continue. So here there are infinite number of elements are there, so that it is infinite set. Okay, so this is about finite and also infinite. Next, cardinality of set. Okay, so cardinality of set is nothing but here number of elements of a set is called cardinality of set. Okay, so suppose here I am taking A is equals to, suppose x, y, z. Okay, so here in this how many elements are there, means here we have 3. So number of elements means cardinality of the set A is 3, and this is denoted by n of A when you are taking set A. So cardinality of the set A is denoted by n of A, and n of A is equals to 3, or you can say mod A is equal to 3. Okay, so simply cardinality of a set means number of elements of a set is the cardinality of set. Okay, right. Next we have equivalent sets. Equivalent sets. So now I am taking two sets. So let A and B be two sets. If number of elements in A is equals to number of elements in B, that means n of A, cardinality of the set A is equals to cardinality of B, then these two sets A and B are called equivalent sets. So here we'll see one example. So here I am taking A is equals to 99, 100 and also here 11, and I am taking B. So here B is equals to 1 minus, minus 1, here minus 2, minus 3, like this I am taking. So here number of elements in A is equals to 3 and number of elements in B is equals to also 3. So number of elements is equals to number of elements in B, so that this A and B are equivalent sets. Okay, so this is about equivalent sets. Next, subset we have. So here it is very important, subset definition. Okay, so here I am taking first two sets here. Let A and B be two sets. Now for every element of A is an element of B. If every element of A is an element of B, then we can say A is subset to B, and it is denoted by this. This is called what? Subset. Then A is subset to B, and here B is superset of A. Here you can write like this. Here B is super than A. Once again I repeat, we are taking first two sets, A and B are two sets, and if every element of A is an element of B, then we can say A is subset of B and B is superset of A. So here first we will see here A is subset of B in the sense, when you are taking an element which is in A, the same element must be exist in B. Okay, so if this is happening for each and every element which is in set A, then we can say the total set A is subset to set B. Okay, so let us see one example, and with that example it's very clear. So here example, so here I am taking symbol 1 2 3 and B is equals to 1 2 3 4 5. Now here all the elements means, for all elements of A means, here 1 is there, 2 is there and 3 is there in B. So every element of A is an element of B, so that this A is subset to B or B is superset to A. Okay, so now we will see, this is very important point here. Note, so number of subsets of a set, number of subsets of a set. Here suppose if cardinality of A is n, or number of elements in set A is n, then number of subsets is equal to 2 power n. Okay, so here we'll see again, if n of A is equals to n, then number of subsets 2 power n. Okay, so here we'll see with example. So here I am taking only one set. Suppose I am taking only 1 comma 2 which are there in A, and now according to the formula here, the number of subset to this set A is 2 power n. So here 2 power 2 means here 4 subsets the subset A contains. Okay, so here number of subset we will write. So here empty set is subset to every set, and set 1 and set 2 and set 1 comma 2. Okay, so here these are the subsets of the set A, because here when you are taking singleton set A, singleton set 1, then every element of this set is an element of set A. So this is subset to A, and next similarly here singleton set 2 is subset to A, because 2 is there in this set itself and also the set A. Here every element of the set 1 comma 2 is of course an element of the set A, because the set 1 comma 2 is set itself. Okay, so here we have to understand one thing, that is empty set is subset to every set, and every set is subset to itself. Okay, so these are the 2 points you must have to remember, and the remaining sets are singleton set or single set with contains 2 elements, so with different examples. So here we will see one more example. Suppose x y z. So here cardinality of A is equals to 3, so the number of subsets of this set is becomes 2 power 3, means here it is equals to 8. So now we will list out all the subset to this set A. Here first of all, as I told you earlier, pi is means empty set is subset to every set, so pi. Next singleton sets we will write, that is x and y, and next z. Next x comma y, I am taking 2 elements at a time and forming a set, that is x comma y, next x comma z, next y comma z, and now all the 2 combinations are completed. Next I will take the 3 combinations. So here x, y, z. So here these are the total 8 number of subset to the set A. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So like this we have to write out. Next type is equal set. Equal sets. So suppose A and B are any 2 sets. Let A and B be 2 sets. If A is subset to B and B is also subset to A, then A is equal to B. Okay, if A is subset to B and B is subset to A, then A is equal to B. This is the equal sets. That means every element of A is an element of B and every element of B is an element of A. Then we can say the 2 sets A and B are equal sets. Okay, so here that means here x which is belongs to A means here that same x which is belongs to B, and here when you are taking x or some other variable y which is belongs to B means here the same variable must be belongs to A. Okay, so here we will see with the example. Suppose I am taking A is equals to 1, 2, 3 and here I am taking B is equals to 3, 1, 2. Okay, so now here each and every element, here 1 is belongs to A, the same 1 is belongs to also B. Here 2 is belongs to A and 2 is belongs to B also, and here 3 is belongs to A and 3 is belongs to B. So every element of set A is an element of B, so here we can say A is subset to B, and similarly here you will get B is subset to A. So hence we can declare that these two are equal sets. That means A is equals to B. Okay, so this is about equal sets. Next, power set. So this is also very important. So power set means it is set of all subsets of a given set. Set of all subsets of a given set is called power set. Okay, and it is denoted by, suppose when you are taking set is A, so given set means here I am taking A is a set. Okay, so is called power set of, I will write here continue, so A, so that is it is denoted by P of A. Okay, so here is very simple. So just now only we have seen the example. So now simply we have to write all the subsets as a set. That set is a power set. Okay, so as I told you earlier, here we have set A which contains 2 elements. So the number of subsets are 2 power 2. So 2 power 2 means 4 subsets are possible. So first I will list out all the subsets for this, and next I will show you how to write power set. So here pi is one subset to A, and singleton set 1 and singleton set 2, and now the elements which contains 1, 2 is also subset to itself. So here these are the subsets of set A. Now these subsets we have to write as one set. So one set means how we will write set? Again we will write these elements and which are separated by commas and which are enclosed by within braces. So here we have to put the braces, and this is called power set of A, so you have to denote with P of A. Okay, so here with respect to the set A, these are the subsets. With respect to set A, these are the subsets, but with respect to power set of A, P of A, these are the elements. Okay, with respect to set A, these are subsets. With respect to power set P of A, these are the elements of the sets. That means here pi is subset to A, but pi is belongs to P of A. There is a difference. Okay, so here suppose here the singleton set 1 is subset to set A, but this singleton set 1 is belongs to P of A element with respect to power set of A. Okay, so now we will see small note and that is very interesting note and as well important also. Suppose when you are taking suppose here I am taking set A and which is equals to pi. Now here pi means it is empty set, so which does not contains any elements. So power set of A. So power set of A means how many elements it will contain means 2 power 0 means 1. So power set of A becomes here pi, singleton set pi. So here singleton set pi is not empty set in P of A. Pi is empty set. Here is a singleton set where pi is empty set. Okay, so just a minute. Pi is empty set. Okay, so now power set of A. So power set of A means here this is considered to be a one set now. So when you are taking this singleton set as one set, empty set is subset to every set. So empty set and the set itself. So now formula also satisfied here. See here P of A, in P of A we have only one element, that is singleton set A, singleton set pi. Now 2 power 1 is equals to 2. So the number of elements in P of A is equals to 2. Okay. So now suppose P of A means power set of A. So here how many elements we have means here 2 elements we have. So when we have 2 elements, the number of subsets of this power set is 2 power 2 means here 4. So now we have to write 4. So see here, first empty set is subset to every set. Next this empty set is also one of the element of P of A. So that element we have to write as singleton set. Okay. So here with respect to pi, with respect to P of A, it is an element. Okay. So here it is set with respect to this. Now here this is also one more element. So here pi, set of pi. So next we have total set pi and singleton set pi. Okay, so totally how many elements we have? 1 2 3 4. So it satisfies. Okay, so like that we can continue and we'll get the number of elements when you are taking empty set as first A. Okay, so this is one very important point here. So next we'll see proper set or proper subset. Okay, so proper subset means here I am taking two sets A, let A and B be two sets. Now every element of A, every element of set A is also an element of B, and this B contains at least one element which is not in A. Then we can say A is proper subset to B, or we can say A is properly contained in set B. Okay, so here we'll see example. A is equals to 1 2 3 and suppose B is equals to, I am taking here 1 2 3 4 5 like this, or we can say we can take only up to 4, no problem. So now in this example it is very clear that every element of set A is an element of set B, and this B contains at least, here we have taken two elements, so at least B must have one element which is not in E. So then we can say A is proper subset to set B. Okay, so this is proper subset. Next, comparable sets or comparability of sets. Comparability of sets. Here, of course, I am taking two sets. Say let A and B be two sets, and if A is subset to B, or B is subset to A, or A is equals to B, if any of these three things are possible, then we can say the two sets are comparable. If none of the thing is possible, then we can say it is not comparable. Okay, so here let us see one example. Here I am taking A is equals to 1, 2, 3, B is equals to here 2, 3, 5, 7. So here it is very clear. Here 1, 2, 3, the set contains the set A contains 1, 2, 3, and here B contains 1, 2, 3, 5, 7. So the element 1 is not in B. So here A is not subset to B, right? And here the element 5, which is not belongs to A, which is in B but which is not in A. So here B is not subset to A, and hence it is A is not equal to B. So it is incomparable. So we cannot compare it. Okay. So this is about comparability of sets. Next, union of sets. Okay. So union of sets. So first of all I am taking two sets. Let A and B be two sets, and union of two sets are denoted by A union B, and which is denoted defined as X such that X which is belongs to A or X which is belongs to B. That means the collection of all the elements which are in A or which are in B or which are in both, means A and B. Okay, once again I repeat, the collection of all the elements which are in A or B or in both elements. So here we can write like this: A union B is equals to X such that X which is belongs to A or X which is belongs to B. Okay, so here we will see one example. Suppose A is equals to 1, 2, 3 I am taking here, and B is equals to 4, 5, 6. Now find A union B. A union B is equals to set of all the elements which are in A and which are in B, or which are in A and B. So here this A and B have different elements. So we will write all the elements. Okay, so here 1, 2, 3, 4, 5, 6. This is A union B. That means here when you are taking a one element which is in A union B, in the sense, if and only if this X which is belongs to A or this X which is belongs to B. Okay, that means A union B is also set when you are taking one element in this A union B, means that element may be which is belongs to A or which is belongs to B or which is may belongs to both the sets A and B. Okay, so we will see that type of example also now. So suppose 1, 2, 3, and here I am taking 3, 2, 5, 7. Okay, so now find A union B. A union B means here set of all the elements which are in A or B and both. So here 1 is an element which is there in A which is not there in B. So now second, 2 is an element in A which is also in B. So write 2 only one time, because repetition of element is immaterial and order is also immaterial in writing set. Okay, so 2, next to 3, next to 5, and this is 7. Okay, so now this is your A union B. So we'll write all the elements which are in A, which are in B, or which are in both. A and B. Okay, so here once again I am telling, when X is an element of A union B, that in the sense this X may be which is in A or which is in B. Okay, so this is what your A union B, union of sets. Next, intersection of sets. Okay, so intersection of sets. Here again as usual I am taking two sets, A and B be two sets, and intersection of two sets is denoted by like this: A intersection of B means and, union means are there, here intersection means and. So A intersection B, and which is defined as X such that X which is belongs to A and X belongs to B. Okay, so here the X must be belongs to both the sets here. Okay, so here when you are taking X is in A intersection B, that means X must be belongs to A and also belongs to B. That is the meaning of A intersection B. Means common elements only we will take in this intersection of sets. Okay, so let us see one example. So here ABC I am taking, and B is equals to, I am taking 1AC like this. So here A intersection B means the elements must be in both the sets. So here A is an element of A, capital A, and also B. So here A will come as an element in A intersection B, and here C is also common element in both the sets A and B. So A intersection B becomes now A comma C. Here the element B which is in A but which is not in B, so that element will not come in intersection B. And here in set B we have only one, so one is an element of B but which is not there in A, so here one also will not come in A intersection B. Okay, so this is about intersection. And now next, disjoint sets. Okay, so now disjoint set means here if A and intersection B is equals to empty set. If A intersection B is equals to pi, then we can say A and B are disjoint sets. Okay, so here we'll see example. A is equals to XYZ and B is equals to 2, 3, 5, 7. Okay, so here A intersection B means here there is no common elements in this A and B, because here A contains alphabets and B contains the numbers, the prime numbers. So here there is no relation at all, so here obviously we will get empty set. So here there is no common elements in set A and also B, so here we can say A and B both are disjoint sets. Okay, so this is another thing. Next, difference of sets. Difference of sets. Okay, so here as usual let A and B be two sets, and difference of two sets is denoted by A minus B, and which is defined as set of all elements in A but not in B. That I will write in terms of symbol and formula. X such that X which is belongs to A and this X does not belongs to B. Okay, that means whenever you are taking an element or X is belongs to X A minus B, means this X belongs to A and does not belongs to B. Okay, if and only if condition is also possible here. Now we'll see one example. So here 1, 2, 3. B is equals to 3 5 7. Now here find A minus B. A minus B means what? Here set of all elements in A but which are not in B. Suppose here I am taking 1 is an element which is belongs to A and which is not belongs to B. So that element will come in set A minus B. Now 2 is an element of A which is not in B. So 2 will come. But come to 3. 3 is an element of A and also element of B. So here we don't consider it because that 3 does not belongs to B, only that element will come in A minus B set. So here A minus B is equals to 1 comma 2. Next find out B minus A also. B minus A means what? Here set of all elements in B which are not in A. Set of all elements in B which are not in A. So here elements in B. So 3 5 7. Here only the element 3 is belongs to A. None of the remaining elements are belongs to A. So the remaining elements will come in this B minus A. So 5 comma 7. So with this example it is very clear that A minus B is not equal to B minus A. Okay. So A minus B and B minus A both are different. Next we have symmetric difference. Okay. So now symmetric difference of two sets here. Again I am taking two sets here, let A and B be two sets. And symmetric difference is denoted by like this: A delta B or A direct sum B. A delta B or A direct sum B, and this A delta B is equals to A minus B union B minus A. Okay. So otherwise here we can write A union B minus A intersection B also. Okay. So that's what our symmetric difference. Okay. So this is the symmetric difference. So now we will see example. A is equals to 2 3 5, B is equals to 7 5 6. Okay. So now find A minus B. So A minus B means the elements which are in A but not in B. So here 2 comma 3. Next B minus A, the elements which are in B but not in A. So here A contains only 5, so and also B. So here 7 comma 6 will come in B minus A set. Now here what? A delta B is equals to what? A minus B union B minus A. So here A minus B means here what? 2 comma 3 union 7 comma 6. So union means what? We'll write all the elements. So here 2 comma 3 comma 7 comma 6 or 6 comma 7 whatever, because order is immaterial in writing set. So this is what our symmetric difference of A delta B. Now here similarly you can check B delta A also. So B delta A means what? Now simply B minus A union A minus B. So B minus A means what here? 7 comma 6 union 2 comma 3 A minus B means. So now here 7 comma 6 comma 2 comma 3. That means what here? Here A delta B is equals to 2 comma 3 comma 7 comma 6, and B delta A also we have got 7 6 2 3. Okay. So if you write everything in order, you will get 2 3 6 7. Here also 2 3 6 7. So both are equal here LHS. So hence RHS are equal. So with this example we can say A delta B is equals to B delta A. Okay. So this is also one of the important point here. Next class we will see the so now universal set. So all sets under consideration are likely to be subsets of a set is called universal set. Okay, that means all sets under the considerations are likely to be subsets of a one set. That set is called universal set. So here universal set will change according to the question. So suppose here when you are taking numbers, the set of all real numbers is the universal set. Okay, suppose when you are taking complex numbers also including all the elements of natural numbers, whole numbers, integers, real numbers, so their complex numbers are universal set. Okay, so here suppose when you are taking only we said V which contains A, I, O, U, now the universal set becomes set of all English alphabets. Okay, so here universal set is denoted by U or here mu, so in these symbols. So next we have complement of sets. So here complement of a set A which is denoted by A dash or A complement, okay, and which is defined as A complement is equals to U minus A, means set of all elements in universal set minus the elements in A. So that means here when you are taking an element which is in A complement, that element which is not belongs to A. Okay, when you are taking element which is in A complement, that element which is not belongs to A. So here we'll see the example. I am taking universal set as 1 2 up to 10 and I am taking A is equals to 2 3 5. Next find A complement is the question. So here A complement means here U minus A, that means set of all elements in universal set minus the elements which are not in A. So not in A in the sense here 1 4 6 7 8 9 10. So this is the A complement. Okay, so here if you clearly observe, when you are taking an element in A complement, that element does not belongs to set A. So this is the complement of sets. So thank you for watching. Thank you. Signing off.